Okay, so today we're going to be doing 7.10, which is going to be base E and natural logarithms. You saw these incidentally a little bit on your Desmos or your Delta Math practice. So it's just a few things that have changed from regular logs, but all the rules remain the same. We just changed the base of the log essentially, okay? So with a natural log, we have different buttons on our calculator for that. We use the ln button, and the e is our base. So log, instead of log, we use the letters ln, which represents the natural log. And instead of having a base of 10, we have a base of e. Now, if you're wondering what e is an approximation of a number called Euler's number. Very similar to a number like pi, which repeats and doesn't have an end, a terminating. It's an irrational number, okay? And the thing about it is we treat it just like any other number, okay? So you treat it just like a number. It's not a variable, okay? It's a number, very different. So we use natural log when we do continuous growth, continuous decay, and we model other things that occur in nature, okay? So this is when we use the natural log, and if you're using one of the standard calculators, it should be a button next to the log. And if you are using the Desmos Scientific, if you go to the function button, you'll see this ln button right here. And above it, you will see an e to the x button. Okay, you see that? ln e to the x. Instead of log, we use ln, and the base of that is e. Alright, so let's go ahead and try some problems involving the natural log. So the first thing we're going to just do is evaluate e. We're just going to practice typing this into the calculator. So we want to do e to the 4th power. So all you have to do is you go to your Desmos, and you type in e to the x. The reason I use e to the x is because I want to put e to some power. And then for the power, I'm going to put in 4. So you see I was able to put in e to the 4th power. And then you just round it based on what the question says. In our case, it's just going to be, we're going to just do 1 decimal place. So I think that's going to be 54.6. Okay? So this is approximately equal to 54.6. Okay? And there's very few e's that we can have that are going to be exact numbers. Usually it's going to be rounded. Okay, so if we go back to our Desmos, now we're just going to change this number right here to a -2, right? Well, that didn't work. I thought it was going to keep it as an exponent, but it didn't. So I'm just going to clear it out. I'm going to go e to the x, and then I'm going to type in -2 to the power of -2. And I get approximately 0.14, right? 0.14. All right, so the next one, we're taking the square root of e to the 3rd power. So how we do that in Desmos is I clear out my calculator, I hit the square root button, and then I go to function, e to the x, and then I can put it to the 3rd power within that square root. And that's going to give me approximately 4.48. And remember, these are all approximations. They are not exact values. So then we have e to the 2/3. So I go back here, I clear it out, I type in e to the power of 2/3. And I get approximately 1.95. Alright, so that's that, pretty straightforward. Now we're going to go ahead and do some operations involving e. So when you see e in a problem, and you see that we have an exponent that we don't know, we're typically going to have to use a log. When we want exponents that we don't know, we use a log. But instead of a regular log, we're typically going to use a natural log to match the e that we have in the problem. So when you see that e come up, you know you're going to use the natural log. So what you're going to do is, when you want to solve for an exponent, you're going to take the ln of both sides instead of the log of both sides. And then we can use the power rule. What do we know happens to the exponent? Goes to the front. And let's talk about what ln of e is. Okay? So what did I say the implied base of a natural log is? E. So this is ln e of e, right? Do we remember back a few lessons ago, what happens when we take the log of its base? It's 1. So this just comes out to be 1, okay, every time. So here's the important thing to know, okay? ln of e is 1. ln of 1 is 0. Those are two that you can automatically just, know when they come up. All right, ln of e comes up a lot. So when that one comes up, you don't have to do anything with it. It just becomes 1. So all I have to do finally to get an approximation for x is take the ln of 9, okay? So I'm going to go into my calculator, and I'm going to clear it out, and I'm going to go to the function button, and you see this ln button here? I'm going to click that, and then I'm going to type in 9, and I get approximately 2.2. So what that means is if I took e and I put it to the power of about 2.2, that should give me about 9. Okay, and you can check your work doing that if you'd like. So let me show you real quick what I mean by that, just so you know. So I want to check my work. I go to the e button and I type in 2.2, e to the 2.2. See how that comes out to be almost 9? So that's a way to check your work as well. Okay, I just put my x back into my original. So this one's pretty straightforward. Am I solving for any exponent here? Is this an exponent? No. So all I have to do is put e to the 7 into the calculator on this one. So I go e to the 7th, and that just comes out to be 1096.6. Okay? Alright, next problem, we have some algebra to do before we can get to the e. So the first thing I'm going to do is I'm going to add 5 to both sides. I end up with e to the negative 2x is equal to 8. And then what am I going to do to both sides? Divide by 4. Okay, so does everyone understand where we got this to be 2? Okay. So now what we're going to do is, remember, we're solving for an exponent. That means we need to take the log of both sides. And like I said, we're going to use the natural log when we're using base e. What's going to happen to that exponent?
It's going to go
Out front. And then what's going to happen with the ln of e? Going to go away because it's just 1, right? And then what's my last step to get the x by itself here? Good. So this just goes away, and I'm left with x is approximately equal to whatever that comes out to be. So I'm going to put this in my calculator, okay? So I go back to my calculator, I clear it out, I go to the ln button, and then I go divided by negative 2. And you should get approximately negative 0.35. And yes, you could check your work on this one too. Just a little more steps to do so. Alright. This problem is very, very similar to number 7. So I'm going to add 12 to both sides. Okay. And then I'm going to divide by 3. So I end up with this, right? Now from here, I can take the what of both sides? Natural log. You're going to start getting the hang of this. What do you see always happens right here? The exponent goes to the front, and what happens to ln to the e? Or ln of e? Cancels out. So isn't this just 4x equals? Yeah. So like I said, when you get better and you're more comfortable with the math, you can skip steps, but don't do it too soon. You know what I'm saying? So this is going to cancel out, and this just leaves me with 4x equals ln of 9. Divide both sides by, oops, that's not what I meant, 4. And I get x is approximately equal to whatever the decimal approximation of this would be. So ln of 9 divided by 4, which gives me 0.55. Alright, so how do you all feel about using E? Pretty easy. Alright. So now we're going to talk about when we have log or natural log in the problem, how we would deal with this. So, when we have log or a natural log of x, this is what you want to do. Equals something. You're going to rewrite it, but you're going to put the base in there. See how I put in the implied base because there wasn't one? So the thing about natural log that differs from regular log, you know how regular log sometimes they'll give you a different base other than 10? Natural log will only ever have a base of e. So there's never going to be like another base given to you in these questions. So now we're going to use the arrow method. You remember this?
Yeah.
So e to the power of 2.1438 is equal to x. And is there any more algebra we can do here? No, the calculator has to do the rest of the work, right? So I pull up my calculator, I clear it out, and I go to e to the x, and then it's it's this, right?
Yeah.
Okay. So when I put that in, I get approximately 8.5. So questions about rounding, I'm just kind of picking tenths or hundredths here. On a test or quiz, you know I will be very specific about that. So just make sure you read the question. Alright, so whenever it's just ln of a number, all you have to do is put this in the calculator. Okay? So you go to your calculator, and I'm going to clear it out, and I'm going to hit the ln button, put in 18. 2.89. Okay. Okay. First thing I need to do here is to get the ln by itself. Divide both sides by 5. So 8 divided by 5 is 1.6. And it's not rounded or anything, that's just what it is. So now I need to rewrite my log with its base in place. Okay? So I just put the base in there. Okay? I divided by 5 and put the base back into my log. Now I can use the arrow method, remember? So that's e to the power of 1.6 is equal to 6x. Divide by 6, and I get x is approximately equal to whatever this gives me in the calculator. So function e to the 1.6 divided by 6, right, is what it is?
Yes.
So here's an easy error that you could make. You hit division before you click out, right? You got to click out and then make sure you do the division. So just be careful. When you're on a test or quiz, just verify that you're doing it right. And you get 0.83. Okay. So here I'm going to divide both sides by 3. I'm going to write my base back into my log. And then I can use the arrow method. And then I'm going to divide both sides by 4. So 745. Just going to round to the whole number here. I don't know why. No reason. Just felt like it. So unless the question specifies, you kind of choose between whole number, tenths, or thousandths, or hundredths. Yeah, don't round to like the nearest like 100 place or anything like that. Like stupid, but you get the idea. Be like 700. No, don't do that. All right. So now we're going to talk about compound interest. So we've talked a little bit about compound interest in this class. Do you remember that formula we used? But we specified compounding quarterly, annually, monthly. Remember we had that period of compounding? This is the formula used called for continuous compounding. If the problem doesn't say these two words in it, these exact two words, you do not use this formula, okay? You only use this formula if the problem says compounded continuously or continuously compounded. Any other time, it's one of the other formulas, okay? So just be very, very careful of that. Just want to make sure you know. So let's talk about what each of these letters represent. A represents the final amount of money you end up with. P represents the starting amount of money that you start with. R represents the annual percentage rate. But remember, you have to convert percents to decimals. And then T represents time in years. Okay? So be careful about that with time. Make sure that it's in years. So if we're talking 24 months, put it into 2 years. Okay? And E is not a variable. It's the E that we were just using on the last problem, approximately 2.71. So yeah, just know that it's not a variable. That's why we never use the letter E as a variable, because it represents a number. Let's try number 13. So suppose you invested $3,000. Is this how much money you started with or how much money you end with? So that's P. Convert your R to a decimal. And then T is going to be the time that we have it in the account for. Okay? So does anyone have any questions about how I identified P, R, and T? So they always have to give you 3 pieces of information to solve for one of the other pieces of information, because there's 4 variables in the problem. So you always need one less than the number of variables in the problem to solve for a variable. So A of 30 is equal to your principal times E to the power of the rate times time. Okay? Now the cool thing about this is if you use the Desmos calculator, I believe it does order of operations for you. Let's check. Because technically you have to do the exponent before you do the multiplication, right? So you want to do this part first. Because E comes before M and PEMDAS, right? So I'm going to check that out. So we do 3,000. Oops, that's weird. It kept my old one. I didn't know it did that. Learning something new every day. So 3,000 E to the power of 0.4 times 30. And then I'm going to try it as a separate step. I'm just testing it out to make sure that the order of operations works in here before I tell you that it does. Yeah, it does. So you can go ahead and just type in the whole entire thing and it will do the math for you. So that comes out to be 9,960.35. So why did I have to do 2 decimal places here? Money. All right. Next question. If $10,000 were deposited into the account, is that your P or your A? P, because that's how much you started with, right? You invested that much into the account. At what rate? So R, we don't know what R is. You see that? We don't know R. Would the account need to grow to have 30,000? What does the 30,000 represent here? A, the final amount. And then 18 represents time. So here, we're not solving for A, we're solving for R. But the thing in math is, they can take out any variable and you can solve for any missing variable. And we now have the tools to do that. So I'm just going to plug into my formula. So I just plug in what I know. E to the power of 18R, right? Because I don't know what R is. So I leave R as a variable. So I just plugged in to the formula. Now, first thing I want to do is I see that I have a variable as an exponent. So I know I'm going to have to use a log to solve here, but I need to get that e by itself. So I divide both sides by 10,000. What is 30,000 divided by 10,000? 3. And now, in order to solve for an exponent, we need to take the what of both sides? Natural log. What's going to happen with this exponent? Move out front. What is ln of e? So if I put this in the calculator right here, that's going to give me my approximate rate. Okay? So sometimes you have to solve for different variables. You're not always going to be solving for a. So realistically, yes, they do use logs to solve missing rates in problems all the time. So ln of 3 divided by 18, yeah, 0.06. But if you want to convert your rate to a percentage, 6%. So this is a realistic problem in life. If you were trying to make a certain amount of money, right, and you can only invest so much, you would want to figure out what rate you need to agree on with a bank to achieve this goal, right? So this would be the math to do that. All right. So number 15, unfortunately I can't zoom it in because it's a long one. If you found an account that paid 5%, convert that to a decimal, compounded continuously, tells me I need to use that formula, and you want to have 30,000. Is that how much you currently have?
No, it's A.
It's A. After 18 years, that represents time. So what we don't know this time is the P, right? So your variables that you're missing are always P-A-R-T, part, the word part. And one of those will always be missing, and you have to solve for it, okay? If it's R or T that you have to solve for, you know you're going to use a log. If it's A or P, most likely you don't have to use the log. So 30,000 equals P times e to the power of the rate times time. Well, I can solve for P by just dividing both sides by e to that power, right? And I can put this whole bit in the calculator to get my P. So I go to my calculator and I clear it out and I type in 30,000 divided by e to the power of, I like to put parentheses when I have multiplication on an exponent, 0.05 times 18, and that's going to give me this amount right here, 12,197.9. Like that. So that means if you wanted to get 30,000 after 18 years, that's the amount you'd have to initially invest. Okay? Alright, so the last problem we're going to do today is going to be a word problem. But I always say if they give you the formula, all you have to do is look for what they're telling you to plug into it. So a spacecraft can attain a stable orbit 300 kilometers above the Earth if and only if, it reaches a velocity of 7.7 kilometers per second. Well, we also have to factor in the mass of the mass ratio of the rocket, the firing time, and the exhaust velocity. And all of these things coming together will get us to a certain height, right? Because if it's heavier, it's going to, affect the speed and all that stuff. There's so many different factors to it. So, as you can see, they gave us R, they gave us T, and they gave us C in the problem, right? Okay. So, let's go ahead and try out the problem. So, we want to see what the velocity will be. So, velocity, we want to see if 7.7 v, velocity, is equal to, and then I'm just going to plug in for everything. Oh, there's another 0 there. Oops. Oh no, did I just exit out? Hang on, I gotta open the new one. Whenever, I gotta take that button off because it's literally like the deadly button. If you hit it, it erases your slide. So my velocity is 7.7 is equal to negative 0.008 or 98 times time plus your C times ln of r. So you see how we were able to plug in for everything? Now, is there any variable to solve for here? No. What we're doing is we're just verifying that both sides of the equal sign basically equal each other, okay, essentially. So I do this calculation on this side right here. Clear it out. And I'm just going to plug in what's on the left here, or the right here. Negative point, oh my gosh, what's going on? There we go. 0.0098 times 100 plus 2.8 times ln of 25. So in that case, we actually reach a velocity of 8, right? So we needed the velocity to be at least 7.7. Has it exceeded that? So the velocity is at 8.03 kilometers per second. So will it reach that height? Yes, it will. So I probably shouldn't have plugged this in here. I was just trying to show you like where that would have went. But basically, if you solve V, you want it to be greater than or equal to 7.7. All right. So yes, it would reach that. Any questions? Okay. You have a solid good amount of time to work on your